Hi everyone, this is Prof. K speaking, and today we're going to talk about quantitative chemical analysis, which is described in chapter 7.5. Our learning objectives for today are to start to describe the fundamental aspects of titrations and gravimetric analysis, as well as start to perform stoichiometric calculations using typical titration and gravimetric data. And so this first video is going to cover this first bullet point and do some highlights of how we begin to do the calculations. And there will be additional videos with actual practice problems worked out. And so to start, what is a quantitative chemical analysis, or what is the definition of that? And so here we have that quantitative chemical analysis is the determination of the amount or concentration of a substance in a sample. And so if we just look at the words that we have here in this definition, we can see that we have quantitative, which looks like quantity. So how much of a given chemical do we have? And the process of determining that is analyzing our compound. And so that's another way we can sort of break down the words to get this definition out. And so what it means in practice is if you go into lab and there's some mystery powder in a whey boat, and you're told that it contains water, copper, and sulfate, but we want to know how much of each it contains, then quantitative chemical analysis is the process by which you determine the amounts or relative concentrations of these atoms in this sample. And so that process can help us get from this mysterious powder to a molecular formula, which tells us that this is copper sulfate that has 5 waters hydrating it. And so this process, quantitative chemical analysis, is sort of the overview topic of the different methods we'll discuss today, being titration and gravimetric analysis. So both titration and gravimetric analysis are examples of ways to do quantitative chemical analysis. And so the first method we talk about is titration analysis. And before I talk about the process, I want to define some of the vocab that we use throughout the process of titration. And so titrant is the substance with a known concentration that we add incrementally to some other solution, our analyte, whose concentration we would like to measure or determine. So we use our titrant to determine the concentration of our analyte. So our analyte is what we're trying to analyze using our titrant, which we are slowly adding in as a titration process. And the tool that we use to slowly add our solution of titrant is a burette, which we've used in lab. And so it's a piece of volumetric glassware that allows us to make these incremental additions of our titrant to our analyte. And so what this looks like in lab is we have some mystery solution that our analyte, which could have some concentration of HCl. So that's all we know about it. But what we want to know is, what is this concentration? How do we describe it? And so the way that we do this is we put this analyte below our burette, our piece of glassware, and we add to this our titrant, which, for example, could be 0.1 molar NaOH. So it's something we know the concentration of. And then we add it in small amounts to our beaker until we see some change or we observe some indication that we've gotten to our equivalence point, which I'll talk about on the next slide. What that does is we dispensed some volume and we underwent some change that we notice. So notice a change. And so in our lab, we used phenolphthalein to change the color of our titrant here from clear to pink. And so that's an example of a potential change you might see here. But ultimately, the point of the titration is that you have some analyte that you're adding your titrant to until you can track some change that indicates that we added enough titrant to balance out the analyte. And the way that we talk about that is using the language of equivalence point. So the equivalence point is the volume of our titrant, or what we're adding, that we require to completely react with the analyte. So if we start here with a 0.1 molarity NaOH, and we have in our beaker, we have a 0.01 molarity HCl, then in order to get to this equivalent point, we're going to need to add some amount of NaOH. And the exact amount to balance this out is called the equivalence point. However, because we aren't always perfect at getting the exact amount of titrant into our beaker that we need to perfectly react with our analyte, we also have the language of endpoint, which is the actual volume of the titrant that we dispense. And so what this is it's how close we can get to the equivalence point. And so ideally, our endpoint ideally equals equivalence point, but that's not always the case. So we have different language for it. So if we look at my diagram, the amount of volume that I dispense tells me the endpoint. But the equivalence point is what I could have done it if I had perfectly balanced out the concentration, which is something you don't know in a lot of the situations because we're trying to determine a concentration. So we don't know exactly where the equivalence point is unless we made the solution and we're trying to test our ability to titrate. And then another specific vocabulary word we like to use around titration is the concept of indicators. And so indicators are special dyes that we add to our sample solution that allows us to see a change in color at or near the equivalence point of the titration. And so if we look back at this slide, I've changed the color here from sort of clear, indicated as blue here, versus pink. And so when we hit the equivalence point, or we've added just the right amount of sodium hydroxide, our solution changes from clear to pink. And that's because we added an indicator here. And so in this solution is an indicator, which is clear at the start of this reaction and turns to pink at the end, which allows us to note that we've hit this equivalence point. And so that's where this sort of indicator is hiding in this process. And so if we looked back at this, at the prior slide, what we can see is that we can calculate the equivalence point or the volume of titrant for our analyte through calculating our endpoint. And so our goal is to try to represent equivalence point using our calculated endpoint. And so if I had some solution of HCl and H2SO4, and I start my burette at 3.15 milliliters, and my final volume is 8.40 milliliters, then my endpoint, or the volume that I have to dispense, is going to be 8.40 minus 3.15 milliliters. And so I get 5.25 milliliters is the volume it takes to reach the endpoint. And hopefully this is close to the equivalence point. That's not something we can know unless we know the concentration of the solution that we start with. And so ultimately, if we refer back to this sort of process table that we had before, what we're using is we're using some volume of solution A to calculate how many moles that we have to react with something in order to use it up. And if we know the balanced chemical equation and that tells us the stoichiometric factor, then we can calculate the moles of B. And if we know the volume of our original solution, we can calculate the molarity as well. And so we can move around on this chart for titration. So we're not doing any new calculation styles, but we're recognizing that we're adding some volume of a solution with a known molarity, and that can help us calculate moles, which we can relate to the analyte that we're using up and determine the moles of the analyte. And so this is just another way to sort of move across this chart using the specific method. And so this is the process for titration, but another method that we can use for quantitative chemical analysis is gravimetric analysis. And so in gravimetric analysis, a sample is subjected to a treatment that causes a change in the physical state of the analyte that permits its separation from the other components of the sample. So one of the processes that we did in lab is that we heated our crucible with alum in it. And what happened is that the water left. So the water sort of comes off and it leaves our solution. And what that is we changed the water from being incorporated into this compound to leaving as water vapor. And so we're inducing a change in the physical state. It allows us to separate the powder in our beaker from the water. And then we can use the masses that we can find in an analytical balance to tell us how much water we lost, or to tell us how much is left of the alum. And so we can use masses to measure different components if we can separate different components. And so heating the crucible is one example where we can get water off of it and do accurate masses. Another thing that we can do is you can pour your beaker into a vacuum filtration process and it will separate solid from liquid. And so then you can get solid, which once again you can mass to see how much you created. And this is a physical state change where you created a solid and you separated it from a liquid that it's in. So we can separate the components of our sample. And then similarly, there's other types of laboratory processes that we haven't done yet in this course, but where, for example, you can heat one sample, produce a gas, which can then leave and react in a different sample. And once again, we can use things like masses and we can analyze different beakers to help us understand how much of the components were separated and what that tells us about the original composition. So if we look back at our flowchart for gravimetric analysis, what we often end up doing is using some mass to help us identify how much of a particular component we have. And then we can relate that particular component to other parts of this process. And so we can say that if we started with if we record a mass of 5 grams of alum, we can use that to tell us how many moles of alum we have. And then we can use that to predict how many moles of sulfate we might produce. And so you can move around this chart again, where we're doing these separations and recording masses and having it help us sort of solve the puzzle of how to move around on this diagram. And so once again, we're still using similar processes, but in order to get a mass, we have to do some sort of separation induced by some change in its physical state. And so that's sort of the important component. And a specific type of gravimetric analysis that we like to use and to talk about is combustion analysis. And so in combustion analysis, a weighed sample. So we mass the sample before we put it in a furnace. And then we heat that sample to a high temperature with excess oxygen. So the whole time we're pouring oxygen over this reaction. And the result is that we get complete combustion to yield gaseous products of known identities. So if you have the combustion of propane, for example, the balanced chemical equation is shown here, 3CO2 plus 4H2O. And so if you combust this completely, if you use up all of the C8H8, then out of the stream comes CO2 and water. And you can use a particular absorber to catch all the water and determine the mass of the water captured. And so once again, we're doing a physical separation of different species. We're recording the masses and then helping us understand how much of our propane we had to start, or potentially what the molecular formula of the propane is. And then similarly, downstream CO2 can be absorbed, and then we can mass of CO2 released. And so if we have these masses, then what we can do is we can return to a slightly reformatted version of our table where you can use the mass of CO2 to calculate a moles of CO2. You can use that to determine the moles of carbon. So for every mole of CO2, we're going to produce 1 mole of carbon. Whereas so this here would have a stoichiometric ratio of 1:1. On the other hand, if we have the mass of H2O, we can use that to calculate moles of H2O. And then for every mole of H2O, we're going to have 2 moles of H, which lets us calculate the moles of H. And then if, for example, we were interested in what the percent composition was of our original gas, then we can use those 2 moles to calculate masses and then use that to calculate percent composition. Or if we weren't sure what gas we burned, we can use our ratio of moles to help us determine an empirical formula. So throughout this process, we're separating different components of what we're interested in, or identifying the quantities of one specific component, and using that to help us understand what is the composition or what is the quantity that we had in our reactants or in some compound. And so all of this is going to be us moving through these charts using dimensional analysis and trying to understand how we can relate what we can record to the chemical information that we're interested in. So we're going to have some practice problems available, and we're going to work through several examples of this so that we can get used to how we do this process and how to make sure that we're doing dimensional analysis correctly for these systems.